Today we're going to think about infinite data structures. So these are data structures that cannot be enumerated. You cannot enumerate its contents like a list, right? So when you think about a list, you could perhaps think about it in terms of comprehension, where you have some kind of set builder notation that tells you how to build a list, or you could just enumerate all the elements of a list, right? You could say, oh, the list has 0, 1, 2, 3, 4, 5. But with a stream, the idea is that it would be an infinite data structure. So it really is just an idea of an infinite sequence of values. They are ordered. And the idea is, how do we implement this so that our code can range over it from one element to the next. So streams exist in many ways. You can think of them, for instance, in network programming, when you have some kind of source of data that is always producing. Could be like a sensor or something like that, that is also always producing elements, values. In this case, could be like reads of temperature or something. But they are used in many more like logical, as a logical notion is also a very strong one. So for instance, in reactive programming, it is that the programming model is such that you are iterating over or reacting to a stream of events. So they could be, for instance, a mouse event or the keyboard event or opening a window, something like that. There's also, as I said before, I talked about networking, but also in stream processing, whenever you have image or video codecs, usually that's the idea, is where you're processing the audio input or some kind of video recording, and you will write code that will iterate over that, and you don't really know a priori how much data there is, or even if you can fit all of it in memory. So usually you have, basically you're operating on a window of data. Also the idea of Unix pipes, where programs output data and then other programs may process this data and pass it along to a next one. Also, there's this idea of Java 8 streams and Microsoft Link, where you can look at a data structure like a collection of values as a stream. It just happens that it's a finite stream of values. Okay, but what we're focusing on is really collections of infinite data, right? So because we cannot allocate it all in memory, we have to somehow constrain its allocation. And the way we can do that is, of course, by means of delaying evaluation, right? So we've learned about thunk as a way of constraining evaluation. So just a function declaration that expects no parameters, zero arguments, or zero parameters. And the way we can build it is, of course, with cons. So you can think of a stream as this very simple recursive data structure that has no base case. This is very important. So a stream is just a pair that takes some value, the value that you're holding in the stream, and the next element, so the right-hand side, will contain a thunk, right, to a stream. So it's a delayed stream there. So for instance, we can start with this powers of 2, where we have a stream that starts with cons, and then you have 1, and then you have thunk, and then 2, and then a thunk, and then 4, thunk, and 8, and so on. It will go on forever. So I have an example of code here that I've already written. So I've implemented this powers of 2. So if I run it, I can show you that the first element of, again, this is a pair. So let me copy paste this representation. Right, so it would be something like this, where you have 1, and then, oops, let me even do it like this. Then you have thunk to 2, that has a thunk to 4, even make it a bit more concise. Okay. And then a thunk to 8, and so on. right? So how would I implement? I mean, I could do this very easily, right? I could implement this just as such. So I could do finite powers of 2, where I could just write cons of 1 and then copy paste this, right? And then here maybe just raise an error saying you went too far. Okay, so here's an example of a thunk, right? So if we wanted just the first 3 powers of 2, I could drag it, call this, and you would just see, you know, cons with 1 and then a procedure, which is this first thunk. But the problem is that this implementation is finite, right? As you know, it only has 1 and then, and then 2 and then 4. It doesn't have even 8, right? So this is what I'm showing you, but I also want to show you that if I were to get the next value, I would get an 8. But of course, as you can see, just by going through with car and CDR, it's quite cumbersome. So you can see to obtain the first element, I do car. And then to obtain the second one, I have to do CDR so that I get this bit right here. And then I have to call it because it's a thunk. So that's why you have the 2 parentheses here. And then finally, I have to do the car to obtain the element on the left. So that would return 2. And then if I want to obtain the 4, I have to do CDR and car of that again. So CDR 2 parentheses, CDR 2 parentheses, and car. So of course, I would like to have a better way of doing this, but this is just to show you that it works. So if I kind of change this to 3, should get an error. Okay, so I get 2, because that's what it is expecting. And if I wanted to obtain 8, I would have to do CDR 2 times, right? Oh, I think I'm missing parentheses. Okay, so it worked as well, just to convince him that this is indeed an 8. So it's expecting an 8, but got a 9. Of course, it should be 8. Okay. So I somehow implemented the infinite data structure, and I read its first 4 values. I also showed you how one could go about and implement it if it were finite. So let's do our first exercise where we want to count how many elements are in the stream up to a certain value. Okay, so in this case, I want to take a stream of powers of 2, and I want to know how many elements are below, you know, are smaller than 8. And the idea is that my count until will count how many elements will match this. And once it does not match, you just return the value. Okay, just to show you how would one think to implement and operate a data structure like such. So what we can do is first let's copy paste the examples. Okay, so now what I want to do, I want to implement define count until, takes a stream, and then it has to return something. So let's just do to do, just to make sure everything is working. Okay, now I get lots of errors, right? So it's saying arithmetic mismatch. Oh, because of course I need my predicate. So I'm going to do predicate here. Okay, so now it's expecting values and it's just returning to do. Okay, so the idea is, how do we get the value? We do car of the stream, right? So in this case, we would need to do a conditional. So let's do that. So we do a conditional. Maybe we even store the value somehow. So the head of the stream is going to be car of the stream. Okay, and then what we need to check if the value is matched by predicate. So if predicate of age holds, then we do something. Otherwise, we do something else. Right? Then we close this, and then we go close this. So if we run this again, now we got something that some branches got this case, some branches didn't. So I got something, something else, something, something else. Okay, because we haven't finished. So if the thing matches, what should we return? If it matches, we should continue, right? Because we want to count how many are, for instance, smaller or equal than 8. So in this case, it's 3. Therefore, well, it should recurse, right? So we want to count until, I want to do as predicate, okay? And this will return some value. And we found one more, so we can do 1 plus whatever value was returned from that. Okay, otherwise, the value has reached the case where this is not smaller than, so let's say it's 8. So if it's 8, what we need to return, well, we know that if it finds 8, then it should return 0, right? Because that doesn't match anymore. So we want to count how many times it matches. Therefore, whenever we do predicate, we add 1. So if we recurse, we get whatever is in the rest of the stream, and eventually we reach the definition. Let's see if this works. Interesting. So let's see, first of all, let's see if the first example works. Okay, of course. What is going on here? So it's blocking forever, right? And this usually tells us that there's something phishing going on. It's just you're not making the stream smaller per se. So how do we make the stream smaller? Basically, we're always going through the first element. And of course, it's always, predicate is always going to be true. And in this case, it's just checking the same element multiple times, right? Because we don't do anything to the stream. So we need to advance the stream somehow. How do we advance it is with the CCDR. So let's do that, right? Because we want the second element, and then we need to evaluate the thunk so that we get the actual stream itself. Okay, so we do that. And it worked, right? It actually ran. So just so that you're convinced, I want to put how many elements are smaller than 10. Should see as well 3. Wait, because 8 also matters. Yeah, sorry. Should be 4. Okay, so now this works. You saw that the test failed and I fixed the number. So there we are. Now let's see if the other things work. Okay, so how many elements are smaller or equal than x? Well, there are 0 elements because the first one fails already. The first one is 1, which is not, and therefore we get to this branch, we get 0, and therefore the whole thing gets 0. Okay, so this is cool. We got an idea of how to operate on a stream. So this is the implementation I wrote. This version is uses a counter to increment the value. In my version, I counted the value after, but both are equivalent in this case. There's no notion of tail recursion here. I mean, actually here there is. Yeah, so this is the non-tail recursive version, and this is tail recursive version. Okay. Next, let's try to implement the powers of 2. So how would we go about and implement this? Let me delete this, pretend you didn't see it. Okay, so now I want to define powers of 2. Okay, and we know that the return is a pair. So this is a function that takes 0 parameters, and when called, it returns a pair. So it should return 1 and then the following value. So as you can see, there's some counter that we need, right? You know, powers of 2. We would like to do something that primes the number. So of course the value that we want to store needs to be stored in some kind of variable, and therefore I'm going to define an internal function. So powers of 2 iter or whatever, or aux for auxiliary, and I want to put the value. And when I want to return is 1 and then powers of 2 aux, where I do n, and I multiply by 2. Okay, so I have here I'm storing the current power of 2. Okay, and of course when I advance it, I have to multiply it by powers of 2, and the element I want to return is going to be a powers of 2. Okay, but this is not correct, right? Because if I try, let me close the parenthesis for now. It's not correct for 2 reasons. The first reason is because I haven't even initialized it. So if I define this function as such, it will return void because define returns void. So instead, I want to return, I want to call this function with the first power of 2, right? So if I want to call it, I need the parentheses. I need to say start with 1. So this is the value going to be stored here. But the problem, this function actually has a bug. And maybe try to pause the video and think about it, why this is wrong. And while you think about that, I'm going to run it. Where's check equal? Oh, I actually forgot to, I removed by mistake. Require rack unit. Okay. Okay, and what you see now is that it hangs. The reason it hangs is there's some infinite recursion going on. Yeah, at some point it uses a lot of memory and the process is killed by the operating system. So what is happening here? Why is this wrong? Well, because we're not delaying evaluation in any way, right? The key point here is that this recursion is happening. There's no base case. So this is just running all the time. So what we need to do is wrap a thunk around this. So if we wrap a thunk, you know, it has to be cons and then thunk. So the second thing has to be a thunk, and it will contain pair because recursively it contains a power of 2, which is a pair. Okay, so technically this should work. Let's see. Yep. Okay, so this is how we implement powers of 2. Yeah, so this version is kind of defined differently, where I place the thunk first. It's just a matter of style, honestly. It doesn't change much. Here there's this trick where you show, not trick, but where you have 2 parentheses, one after the other, doesn't show up. So I kind of like this style a bit more now. But this is what I have in the slides. Okay, in the next slide, in the next video, we're going to think about how to build a stream of constants, of a stream that always returns the same value.